My name is Abdurrauf Kityan and I am here to present our work entitled Exploiting the Progress of Object-Oriented Refactoring Tools with Android Code Smells, RAndroid, a plugin for Android Studio, as part of the SAC 2021 poster exhibit. It all started with Fowler when he introduced refactoring as code restructuration while preserving the external behavior, then associated the name code smells with bad practices which imply the degradation of applications quality. At that moment, Fowler opened a whole new aspect for researchers to study, an aspect that we found full of opportunities and motivations. For example, researchers has proven that a large number of code smells are correlated with bugs and maintainability issues, therefore with code quality and applications performance, which is the reason that 75% of Android code applications are uninstalled within 3 months, an issue that we saw as an opportunity, especially with the lack of Android-specific refactoring tools. We found out that several Android-specific code smells detection tools have emerged in recent years, such as Paprika and iDoctor. However, the refactoring of these smells is carried out manually in most cases. On the other side, several object-oriented refactoring tools such as Geodeodorant and Gsmell are developed yet not exploited to deal with the Android code smells. It's interesting as well to mention the fact that the latest statistics done by StatCounter website declares that Android controls over 72.6% of smartphones worldwide. Anyhow, all once we saw those opportunities, we started asking questions. Yet the question that intrigued us the most was how can we exploit the Android code smell detection tools and adapt the object-oriented refactoring tools to eliminate code smells on the Android platform automatically after their detection, which resumes the problematic that we are trying to cover in here. In order to resolve this problematic, we had to determine and follow a specific process, starting by exploiting the progress made in object-oriented refactoring tools by selecting the most effective tool with the aim to adapt it to refactor Android-specific code smells. We studied the existing tools and the empirical studies that compare between them, like the one done by Fontana. We also made our own study comparing between two object-oriented refactoring tools. In the end, the tool that we chose for our work is Geodeodorant because compared to the other tools, it has shown better results in addition to the fact that it is open source, which makes it possible for us to adapt its code for our work. After that, we studied and selected the code smells to be handled in our tool by elimination based on detection metrics, uh, uh, impact on resources, and ensuring diversity regarding the classes defined by hashed. Our selection process also ensures that the code smells chosen aren't deprecated or already refactored by other tools. Furthermore, we took into account the fact whether these code smells are detectable by any Android detection tools or not. The five code smells that we ended up choosing are IOD in its own row, HSS heavy service start, and RAM rigid alarm manager, IDS inefficient data structures, and UIO, which is UI overthrow. Then, since we decided to focus on refactoring specifically, our Android plugin has to be connected to an external detection tool, which indicates the type, number, and location of code smells. The detection tools that we choose must be able to detect the code smells that we are refactoring using our Android. Therefore, we use the two tools, Paprika and a Doctor, because they are open source, well known, and cover diverse code smells, including the ones we are covering. And finally, to adopt Geodeodorant refactoring models in order to correctly refactor Android-specific code smells, we had to adopt the logic behind the creation of syntactic and semantic code smell model used in Geodeodorant IntelliJ version. To properly use the PSI, which is the Problem Structure Interface API, in analyzing Android's code, we have applied a few changes and adjustment in the used refactoring algorithms while preserving the architecture using the exported part. We adapted it by adding some new methods in order to fit with Android projects. After studying each code smell and then understanding its triggers and the problem it causes, we decided to apply refactoring based on the techniques proposed by Fowler and already implemented in GDNorrent, like extract method, substitute algorithm, and other techniques. We proposed a different approach for each code smell. Taking IOD, for example, according to Habshi, a large number of IOD instances are eliminated when a few specific modifications are applied. The changes specifically removed the allocation or removed it from the on-row method. On this basis, we went with extracting the allocation instances in addition to any long treatment inside the on-row method by applying the extract method refactoring technique to move these sections from the on-row method to another positionment. For HSS, we proposed embracing the content of onStart command in a new thread of our own creation, applying the refactoring techniques of algorithm. For RAM, we went with extracting the set repeating and replacing them by setting exact repeating using substitute algorithm refactoring technique. And while for IDS, we went with detecting all occurrences of hash map whose key is type integer or long, then uses the refactoring technique substitute algorithm to replace those occurrences by a sparse array instance, while handling all necessary changes to ensure that the external behavior won't be affected. So in order to apply these approaches, we went with the following architecture. As the figure shows, our tool has two main input. One, the CSV files containing the results of one or more of one of the two detection tools, Paprika and iDoctor, that we use to help us determine the location of code smells. And two, the application source code itself, since the tool needs to precisely determine the instances, location, and deal with them, while the output is limited to the refactored source code. And once the detection files are available, user interface model intervenes to present them as data to our system by managing all user interactions. They are usually handled through another layer, which is represented as Android Studio Action System, which represents the communication interface between the user and the tool. When the files are presented, the detection model starts its job by reading them, detecting the exact location of each code smell instance by analyzing the entities, which are the classes and methods found in the input file. After that, it stores all their location in a special collection handled uh, in a special collection. Then we pass this collection to the refactor model, the corrector model, which will either refactor the code smell or give recommendations based on the code smell. Other than that, there is another model, which is adapted JDorant, which represents the communication interface between our RAndroid and the code base itself, allowing us to apply our refactoring approaches. In order to measure the accuracy of our tool, we follow the specific process in order to achieve a set of goals, which are first, check whether the approaches we followed in our solution do really handle those code smells, and second, to check whether RAndroid covers the studied cases without adding any bugs or changes that impacts the external behavior. We started by analyzing more than 120 applications developed in Java by developers from different backgrounds and levels of expertise using the two detection tools, Paprika and iDoctor, of course. Only 52 Android applications contained one or more instances of the studied code smells. After the detection phase, we applied our approaches on each code smell instance, 194 code smell instances to be exact, then went through a second phase of detection. The third step is to compare between the detection results to know if the first goal is applied or not. After that, we checked recommendations if our approach left any, and finally, we verified the impact our changes left on the external behavior by checking if our test cases passed or not while analyzing the reason behind any encountered issues. Our solution managed to fix 50 out of 55 IDS instance, 18 out of 19 HSS instance, 34 out of 37 IOD instance, and all RAM instances. It also managed to give dynamic recommendations for 38 UIO instances out of 46. Overall, our solution managed to cover 91.24% of the code smells. Therefore, I think it's fair to say that our solution was successfully able to handle the 5 code smells without causing any serious bugs that would harm the performance of the external behavior of the applications. We can't deny that it showed some issues and caused some bugs, yet this happened in only a few cases. We made sure to study these cases and understand them for future enhancements. And gladly, since we have built RAndroid based on solid principles and design patterns in order to ensure the scalability, flexibility, and maintainability, this made it open to all kinds of improvements. In future works, we would mainly focus on integrating the tools into a full detection and refactoring process. We also plan to scale the set of code smells to more than 5, developing new algorithms and refactoring solutions, of course. And finally, thank you for your attention and thank you for your time.